Alright guys, so what we're going to do now is we're going to look at some actual applications of parametric functions. So what I'm going to do is I have a word problem here. I have a cannon that's shooting from ground level at an angle of 37 degrees with an initial velocity of 300 feet per second. So I'm going to draw out what that looks like. I've got a cannon, and I know that that cannon's going to shoot up, and then eventually it's going to come back down. And I know that that angle was 37 degrees. What parametric functions can help us do is actually write an equation for the path of this cannon a lot simpler than if I was using just regular old equations. And I can make changes to them much easier, because at every point on this line, there's an x component and there's a y component at a certain time. So what I'm going to do is I'm going to write an x equals equation to talk about where that cannonball is horizontally, and I'm going to write a y equals equation to talk about where it is vertically. So to come up with that x equals equation, to take any point on this graph, no matter where it is, and get that x equals equation, I can use my speed times the cosine of that angle. And what that's going to do is if I want to find that at a specific time, multiply it by t. So that helps me to figure out at any point, at any time, I can plug in for t and figure out where that cannonball is horizontally. And remember, I'm using cosine. Cosine goes with my x because it's the adjacent of that triangle. All right, let's say I want a vertical spot, though. A vertical spot at any point on here at 37 degrees, I'm going to want to use sine. And again, I'm going to want to multiply this by t to see at what time it is. Now, the only other thing I have to consider here is if I don't incorporate something else, that cannonball is going to go up in the air forever. There is something that's bringing that cannonball back to the ground, and that's gravity. So just like every other time you had to do that negative 1/2 at squared, I still have to incorporate this here. And because I'm using feet per second, I'm using 16 instead of 9.8. So what I'm going to do now is I'm actually going to graph this on my calculator so you guys can see what this looks like. So I have my equations, 300 cosine of 37t, 300 sine of 37t minus 16t squared. One thing to make sure of, though, I did the sine of 37 degrees, so my mode needs to be changed to degrees. Now I'm going to look at my window. I need to make sure my Tmin and my Tmax is going to be big enough to cover the amount of time that cannonball is in the air. So hopefully it's going to be in the air less than 10 seconds. My Xmax is the horizontal distance this cannonball travels. So I'm just going to guess a random number and see how far it goes. Okay, it's probably going to be more than 300, but I just picked a number to start. Ymin is 0 because it's starting at the ground. And my Ymax is how high it's going to go. And again, I'm just going to pick a random number and see what happens. Alright, so if you look at my graph, it's not hitting the ground yet, so I need to make my Xmax bigger. So let's change that Xmax to 700. Alright, still not enough on my graph. Okay, so let's make it even bigger. Let's make this 1500. And now let's look at my graph. Alright, still need to make this even bigger. So let's look at our table and see how far this is going to go before I keep guessing and checking. So if you look, my x values are here and those y values are here. So it looks like the highest it's going to go is about 500. And then it's going to hit the ground after 11 seconds. So I'm going to make a couple changes here. I'm going to make my Tmax a little bigger. I'm going to make my Xmax a lot bigger. And I'm going to make my Ymax bigger. And now let's see if I can see my whole cannonball. And there it is, there's the path of my cannonball. Now if I want to, I can trace on this and I can see at a certain time where it is. At a time of 1.2 seconds, there's my x distance, there's my y distance. the next question I had on there was, when is that cannonball 500 feet away? So I can do that a couple different ways. Okay, I can use my calculator, or I can do this algebraically. I want to know when it's 500 feet away horizontally. So in order to do that, I can just use my x equation. So I want to know when 500 is equal to 300 cosine 37 times t. So in order to get t by itself, I just need to divide by 300 cosine 37 and type that in my calculator. And when I do that, and make sure you check your parentheses here, I'm dividing by the 300 and the cosine of 37. So that gives me my time of 2.18 seconds. Alright, so now what I'm going to do is I'm going to make a couple of changes to these equations. So instead, I'm going to take that same speed of a cannon at the same angle, but now I'm going to make that cannon 4 feet above the ground. So what's nice about these parametric equations is they're much easier to change. I can take my original equations, and then if it's going to be 4 feet above the ground, that's not going to change my x component, that's only going to change my y component. So if I want to, I can just add plus 4 to my y. Alright, let's say I have this next part. It says there's a wind 10 feet a second behind the cannonball, so going with the cannonball. So as that wind, it's not going to change the y component, it's only going to change the x component. So I can keep my original equation, but now I'm just going to incorporate that wind that's going to change the x. Because it's behind the cannonball and with the cannonball, it's going to increase the speed. So we're going to add to it. And because it's a speed, I need to make sure I don't just put plus 10. It's a speed, which means I need to put plus 10t. Alright, now the last thing we're going to look at is we're going to see if this cannonball can clear a wall. So what we're going to do is we're going to have a wall that's 2,500 feet away at a height of 120 feet. And what we're going to do is we're actually going to graph we're going to graph that wall as in a parametric equation. So what I'm going to do is I'm going to come up with a way to write this. I'm going to have an x equals component and a y equals component. Now the x equals, a wall is going to be a vertical line. So that x part isn't going to change. That x is going to be the same for everything. So what I need to do is come up with a number for that x. If that wall is 2,500 feet away, that x coordinate is going to be 2,500. I don't need a variable because it's not going to change. Now the y is going to matter. I need that y to change though so that I'm going to have some height of this wall. Now what's interesting here is that y component is going to be dependent on what your t min and max are. So if I have a t max of, let's say 10, that y needs to go up to 120. So I need to make that y 12t, so that when I plug in the highest t value, I get 120. But let's say instead I have a t max, if my t max was 1. If my t max was 1, then my y equals equation would have to be 120t. Alright, if my t max was 12, then my y equals equation would have to be 10t. So the t max I used was 12, so I'm going to go ahead and graph that equation right there. And we're going to see if this cannonball is going to clear the wall. Now what I'm going to do is I'm going to change this mode back to sequential, so I draw the wall first. Alright, so I have my wall equation first, and then I have my equation for my cannonball, and we'll go ahead and graph it. So here's my wall, and you can see there's the cannonball, and it goes up, and it goes over, and it doesn't hit the wall. Alright, what if we were to change something here? What if we took off the wind? Let's see if that would make a difference. So I'm going to take that plus 10t and get rid of that. Now let's see if it makes it. There's my wall, and there's my cannonball, and it's really close. So if we want, we can zoom in and we can see. And then we can see a little bit closer. There's the top of my wall. And then slowly there goes my cannonball. And you can see it doesn't touch it even without the wind. Alright, so that's just a couple different applications of parametric functions, so you guys can use parametric functions to help you solve word problems now.